Great. So thanks for coming to day 3 of the 6th Bath-Beijing-Paris meeting. And to start off the day, we've got Zhenyao who's going to talk to us about effective small noise on the speed of reaction diffusion equations with non-Lipschitz drift. So thank you very much, Zhenyao.
Okay, thank you, Sarah, and thanks very much for the invitation. And what I'm going to talk about is this model called the stochastic reaction diffusion equation. Wait, I'll get to the next page. Okay, I need to figure out how I get to the next page. Okay, maybe I just do it in this way. But I'm going to start with probably a very simple model, one of this reaction diffusion equation, which is the stochastic FKBP equation. So essentially you have this FKBP equation here, and you add a noise, which is the Wright-Fisher white noise. And we also have a parameter epsilon here, which we call the noise strings. So later on, this noise string is going to be changing. And I want to start with this simple model and just to maybe tell you guys about a little bit of the background and the thing we already know. So I want to emphasize here that this SPDE, we are considering it just on the one-dimensional case. So you don't have this irregularity for the high-dimensional SPDE. You can, for this SPDE, you have actually different ways to make sense of the solution concepts. One way is to consider it as its integral form, or you can call it melt form, or you can treat U as a general function or Schwarz distribution, or you can consider the corresponding modeling problem of this SPDE. They are all equivalent, but just for this stochastic FKBP equation, there's actually another way to characterize its solution, and it's called to treat it as the dual process of a particle system called branching coalescing Brownian motion. So in any, just by using any of one of those solution concepts, you can come up with this nice result about the solution by Shiga and Mueller and the solvers, and they proved that the solution of this SPDE, you have the existence and the uniqueness in law of the solution of this SPDE in this function space Ci. So what is Ci? Ci is the space of the continuous functions taking values between 0 and 1 who has compact interface. So what is a compact interface? When we say a function has compact interface, we mean that there is a compact set, compact interval actually. On the right-hand side of that interval, the function always taking value of 0, and on the left-hand side of that interval, the function always take value of 1. And this theory actually, so you can kind of think of this theory as telling you that UT is a marker process who take values in this space Ci. So at any time t, UTX well looks like this. Okay. So in the real world application, you might think the UTX as like the proportion of the variables maybe at a certain position X. Then on the left-hand side, all the population are infected. And on the right-hand side, all the population are like not being infected, they are healthy. And we want to understand, what we want to understand is how this interface between the infected population and the non-infected population, how this interface evolve while time goes to infinity, right? So that's what we want to understand. So you have these very nice results by Mueller solver in 1995. They proved for small enough epsilon, and later by Collin and Doring, they proved for all the noise strings epsilon there. The right edge or you can say the front of this interface, RT, actually have a deterministic speed. You can think of it traveling to the right with a deterministic speed, which we denote by V epsilon. Okay, so this is quite a nice result, but it doesn't tell you what the speed is, what is the speed, right? So I want to show you guys some information we know about the speed V epsilon. So first of all, we don't actually know the precise a formula for the V epsilon. It's still unknown, but what we do know is that the V epsilon, we have a lower bound and upper bound for this speed V epsilon. So just by the comparison of the SPDE, you can prove that the speed has to be positive. But you also have a upper bound, which is √2. So this √2 is actually very important because this speed is actually the speed of a standard binary branching Brown motion. So some of you already very familiar that the deterministic FKBP equation has a very close relation to the binary branching Brown motion. And that's exactly why we can compare the speed of this model with the branching Brown motion and get this upper bound. I will be more precise later about this. And what we also know about V epsilon is this asymptotic behavior when epsilon goes to either infinity or goes to 0. Okay, so when epsilon goes to 0, it turns out that the speed will converge to the speed of √2. By the way, the √2 is also the speed of the traveling wave solution of this FKBP equation. So, but what is very interesting is that the rate of this Y epsilon converging to this constant is really slow. It's unusually slow. Okay, so it's being predicted by these two guys, Bern and Derrida, that the V epsilon should have this type of behavior when epsilon is small. And later, it's been proved by Mueller, Minnick, and Constable that this is actually holds. And Bern and Derrida, they actually kind of predicted this type of behavior for a very large family of models, including the branching coalescing Brownian motion, which we mentioned is the duality process of this model. But they also predict this result for other models, like just name a few, like the M branching Brownian motion or the L branching Brownian motion. So to be honest, I'm not really familiar with this, but fortunately we have a lot of experts in the audience right now here. So maybe you can ask them for more details. Okay, so when epsilon goes to epsilon behaves like the 1 over the square root of the epsilon. So this has been conjectured by Colin and Doran, and then later been proved very recently by Mueller, Minnick, and Rijik. Okay. So now let me be more precise about this duality formula for this as PBE. So I want to introduce you guys this particle system branching coalescing Brownian motion, and I want to talk about its duality. And from this duality, it's kind of more clear why the speed V epsilon has to be smaller than 1 square root of 2. So what is the branching coalescing Brownian motion? So it essentially is a branching Brownian motion with an additional rule that each pair of the particles in the system will coalesce into one particle according to their intersection local time with rate, which is epsilon square of the epsilon. So for example, we have this particle system here, and each particle might branch into 2 particles with rate 1. And each pair of the particle here, the blue particle and the red particle, they might meet with each other. And when they do that, their intersection local time is going to be accumulating. And when that intersection local time accumulates to an exponential clock, these two particles will coalesce together and becoming actually one particle. So if you consider this particle system and if you denote the IT as the index of the particles alive at time t and xt as the position of particles at time t, then Shiga proved this duality, proved the duality between this model to the SPDE UTX, and it looks like this. If you take an independent weak solution UTX to our stochastic FKBB equation, the expectation value of 1 minus UT, the product of the expectation of the product of the 1 minus UT at the position of the particle at time 0 actually equals to the expectation of the products of the 1 minus U0 at the position of the particle at time t. So you have this nice duality formula for these two models. So what this duality tells us is that it actually characterizes the finite movements of our solution UT. So because it characterizes all the finite movements, it gives you the distribution of UT, and that's how Shiga proved the weak uniqueness for the SPDE. And the other thing that it actually also characterized, so if you take the initial value of the SPDE by this heavy-sided data, you can actually have this formula for the rightmost particle, for the distribution of the rightmost particle for our particle system, for our branching coalescing ground motion. Because of this, we kind of know that the propagation speed of this particle system is actually closely related to the propagation speed to the SPDE. And since this coalescing, the speed of this particle system has to be smaller than the non-coalescing counterpart, right? The non-coalescing branching ground motion, which actually propagates with speed of square root of 2. So that's why we know that the speed of the SPD is smaller than square root of 2. Okay, nice. That's kind of like the background for the stochastic FKBP equation. And now what we want to do is we want to consider more general drift for this equation. So we want to consider more general reaction term for our reaction diffusion equation. So if you forget about the noise for the moment, just think about the deterministic case. So in the real application, there actually a motivation for doing that. So in the real application, people are interested in the reaction diffusion equation with more general drift FU. So in this paper, in this review paper, the authors, they actually classified this type of equation by their reaction term. And they have this type A, B, and C, 3 types of reaction. And the type A reaction is, you can see the FKBP equation is in the type A. So what is this? This is the graph of the function f of u. Okay, so you kind of have like these 3 types of reaction term, and they are what is in common with them is that they are all Lipschitz. They are all Lipschitz kind of drift function. So you can see that they are actually classified according to their behavior, according to the behavior of the drift when u is very small. So type A corresponding to a positive derivative of fu at 0. And type B, you can see the derivative is 0 here. And type C is that you have a negative derivative. So for all those cases, when f is Lipschitz, in many cases when f is Lipschitz, our reaction diffusion equation actually all have finite propagation speed. So it's meaning that their speed, their solution u will travel kind of like with a finite speed to probably converging to a traveling wave solution. But what you can also do is you can consider the reaction diffusion equation with even more general drift when Fu is not Lipschitz anymore. So in this paper, 1986 paper by Aguri and Escobedo, they consider this non-Lipschitz drift, and they prove that actually for this deterministic reaction diffusion equation, you don't have finite speed anymore. You have like if you're thinking it as a traveling wave, again, then you will have like infinite speed. Of course, you can also consider, what you can also consider is the more general stochastic reaction diffusion equation. So what you do is you change the FKBP drift and also the right Fisher noise into more general form. So here as Ria and Tri, we consider this case when F and the square root of sigma are Lipschitz, and they prove that for this model, for a large class of this model, they actually have this duality relation to this branching coalescing they have this duality relation to some branching coalescing type particle system. And immediately they have the weak uniqueness of the solution, and they can see a lot about this model. And just to mention that the results here, most of the results here also holds for this model when the sigma is comparable to the right Fisher noise. But what we want to think about is the stochastic reaction diffusion equation when the drift is actually being taken as non-Lipschitz function here. So just remember that as we are trying, they consider the Lipschitz case. So if you take this Holder continuous drift, so you have a picture like this, it's not quite known that if this duality still holds, even though we have like we have reasonably believe that this duality should hold. That what I mean is that this SPDE should be the duality to some branching coalescing boundary motion. So here is the conjecture that for this drift, they're actually corresponding to a branching coalescing boundary motion whose offspring law has this form. So this offspring law will have like infinite mean. So it's not going to be like the classical branching coalescing boundary motion. So even though you don't have this duality holds, people can still study this SPDE just by using the tools from the stochastic analysis. So this is a very recent paper by Müller, Minnick, and Rijik. And they studied this SPDE with a general drift, Fu. And their assumption on Fu is that F is going to be a continuous function, and F will be controlled by this square root of U times 1 minus U. Or you can see the drift F will be controlled by the noise term. So just to look at this condition, it's actually a very general condition because it actually includes all those three types A, B, and C, but it also includes some of this non-Lipschitz case. So especially it includes the case like U to the P times 1 minus U, when P take the value between 1/2 and 1. So up to now, we don't know anything about when P is smaller than 1/2, but we do know this result when P is greater than 1/2. So what they proved that what is their result? They proved that this model still have weak uniqueness, still have weak existence and weak uniqueness in the same function space, Ci, which just to remind you guys, it's a continuous function with compact interface. And we can also prove that actually this interface, the front of this interface, have a finite speed, V epsilon, right? So this is actually very interesting because if you don't have this noise and if the drift F is Holder, so this function, this deterministic function will actually have infinite speed. But now after you introducing this noise, you suddenly start to have the finite speed. Okay, so this is really interesting actually. So but we still know very little about the speed v epsilon. Okay, so people might want to ask what we know about this speed. So all of this is what we know so far. So first of all, we don't have the precise expression for the speed. Again, we don't know what it is basically. And also we don't know the upper bound for this speed. So basically, we think that when epsilon goes to 0, the speed might converging to the deterministic equation, the speed of deterministic equation, which doesn't have speed, right? So we actually don't have any upper bound. But we do have, what we do have is the asymptotic behavior of this speed when epsilon is very small or when epsilon is very large. So here's the result by Müller, Minnick, and Rijik. And they consider the case when epsilon is very huge. And they proved that the speed with epsilon actually behaves like a 1 over square of the epsilon. So this is actually the same behavior as the stochastic FKB equation. So basically, if you have a very huge noise coefficient epsilon, it doesn't really matter if your drift is a holder or is a Lipschitz or not. The speed always behaves like this. But here is a new result which I want to present to you guys.
Sorry, just to say, there's a question in the chat from Zhenyao saying, "Do you have convergence to a stationary state seen from RT?"
You have like a stationary. Repeat that again. So
it says, "Do you have convergence to a stationary state seen from RT?" So seen from
yeah, we don't know that yet. Yeah, so that's an open question. Of course, we believe that that should be true. Yeah,
it's not in the Lipschitz case, right?
Yeah, of course. In the Lipschitz case, we do know the result of the converging. Actually, just for some precise case, not every Lipschitz case.
Okay. Okay. Thanks.
Okay. So let me continue by present you guys our result. So our drift function, we still assume that it actually satisfies the condition by the 3 guys, so that you have the solution, you have this unique in-law solution. And if you know that the drift, additionally, if you know that the drift behaves like the function u to the p when u is very small, then you kind of know that the speed of the v will behave like the epsilon to this exponent, to the -2 times 1 minus p over 1 plus p. So that's what our result trying to say. So we prove that if the limit infimum of u to the minus p times fu is strictly positive, then the limit infimum when epsilon goes to 0 of this epsilon to this exponent times the speed will also be strictly positive. So similarly, if you change the limit infimum as supremum, we prove that if the limit supremum is smaller than infinity, then the corresponding limit supremum of this formula was strictly smaller than infinity. So just take an example. If we take Fu as this holder continuous drift, then and of course we want our P will strictly larger be 1/2, because when P is smaller than 1/2, we don't know the solution existence of, we don't know the uniqueness of the solution. And then what we know is that the speed will be comparable to this function, epsilon to the -2 times 1 minus P over 1 plus P. Okay, so our main contribution is just to identify this exponent here, because it is showing in both lower bound and upper bound, so you cannot improve this exponent. Okay, so that's the main result. Let me just give you some very quick, maybe a little bit comments on how the proof strategy. So what we do is we decompose the solution U into 2 parts. and one is one is the what we call V, is the actually satisfy exactly the same equation, except that it will be killed at a moving boundary. So we actually artificially imposing a linear moving killing boundary with the speed V star, and we get a new random field V, and what's left is a random field W. So this technique is actually very common when you are trying to figure out the speed. I think it's yesterday, Jason also mentioned a lot about killing at the boundary. If you, just from this picture, you can see that if you choose this speed V star being really large, really huge, then this W will actually have will actually be really small, because if V star is really large, larger than the speed of RT, you don't have a lot of space for this W to survive, right? So W should be small. And if V star is very small, then W will actually be very large, and W will propagate with the speed actually. So what we do is we want to find this critical value for V star, so that this random field W will not be too small and also not be too large. Okay, neither too small or too large. So we're actually finding some critical value V star here. So it's kind of for the people who study this, for the physicists, they studied particle systems, they kind of have some intuition behind it. And so one of their intuitions says that this critical value V star can actually be predicted by solving certain system of PDE here. So what is this PDE? It's actually the same equation here, just without the noise. So you have the same equation here without the noise. But we are trying to solve this equation with a free boundary, meaning that the boundary is also part of the solution. And we are trying to find out the traveling wave solution. And we take the derivative at zero of this wave profile be related to this noise strength square root of epsilon. So this condition is not that important, but so the second condition not that important, but you can solve this. The point is that you can solve this as PDE, and the speed we start here will be a good prediction of the critical value for this random field W. So basically, we can solve this equation, which gives us not precisely when I'm saying that we can solve it. It's like we can kind of calculate the eccentricity of this V star, and it actually gives us the our result here. So I would say this is probably the most important step, because before you know the exponent here, you don't even know how to what kind of result you want to do. But after you predicted something, it's like we will have a lot of tools to apply here to get the result. So basically that's the main story. So I will probably stop here by mentioning my collaborator, Leonid Minnick, and another postdoc of him, Clayton Barnes. And thank you very much.
Thanks very much. So we're a little bit short on time. So if anyone has a quick question, or if not, maybe we should, oh yeah, Pascal, do you want to go ahead?
Yeah, I have a quick question. So so you mentioned that it's not known whether you have the duality with a branching coalescing system with offspring distribution of infinite mean. So at least when there is no noise term, then it's clear, right? So then there is duality with branching with this offspring distribution. And yeah, I find this quite intriguing actually, because I'm not aware of many works on branching Brownian motion with offspring distribution of infinite mean. So can you give me some references on that?
Yeah. Just like you mentioned, we do have the duality. We kind of have, so you know what, actually, by dualities, you have to be careful because for this model with infinite mean, with the upstream law with infinite mean, you might have explosion for the model. So you might have actually infinite many particles at a finite time. And by that, I mean explosion at a local space, you know, it's not like the total number exploding. It's like it's becoming infinity everywhere. So it's, but you can still kind of like by using the monotonicity, you can kind of see you do have the duality because you can see, okay, the solution are increasing, the solution are monotonically increasing or something, the particle system are also monotonically increasing. So for the deterministic equation, we do kind of have this duality, or you can see that. It's just maybe most of the case, you have like infinite many products, so you have like 0 equals to 0 or something. But I think that that's for the deterministic case. This is a conjecture just for the stochastic case, yeah.
Okay, thanks.
So I see that Zhenyao also has his hand up, but we are running a little bit late. So Zhenyao, would you mind if we leave it to the coffee break?
No problem.
So thanks Zhenyao very much again for his lovely talk and beautifully written slides.
Okay, so how I quit this sharing? Stop share.
I think you should be able to press stop share. So I think next we have Emmanuel.
Yes. Right. Oh,
Yeah.
I should make him. Yes, your co-host now, Emmanuel.
Okay. Can you see my screen?
Yes, we can. Yep.
Okay.
Brilliant.
Yeah.
Okay, great. So now we've got Emmanuel Schertzer, who's going to speak about probabilistic models related to the SARS-CoV-2 pandemic. So thank you very much.
Okay, thank you very much for the invitation. So I will talk about the joint work with Félix Foucault-Rodier, who was a PhD student of Amaury and myself a year ago now, almost a year ago, and Jean-Gilles Duchamp, who is maître de conférence at Besançon. So just to give some brief motivation about what I will talk about today. So I think we're all convinced by now that the life cycle of the COVID-19 virus is quite complicated. So here I just gave you a rather detailed example of a description of this life cycle. So if you look at the lower branch, so this corresponds to individuals that get infected with mild symptoms. So they are recovered after being sick for a few days. And the upper branching corresponds to what happens if you go to the hospital. And again, from here, this can get a bit complex. Either you recovered after like a few days, or you go to ICU and well, either you recover or you can die from the disease, right? So, and of course, this can get even more complicated. And so the moral of the story here is that if you want to make a good model for these epidemics, then you need to take into account a lot of compartments. And of course, this looks much more complicated than the toy model, like the SIR models that we all know from a long time ago, right? So what I would like to do here is to propose like a class of models that kind of incorporate in a nice way those different layers of complexity, right? And so it's not a model, it's more like a framework. And in this framework, I will distinguish mainly between two types of individuals. So either you're susceptible, okay, so you have never been infected before, or you're infected. And by infected, I mean something slightly different than what it is usually meant. So more precisely, what I mean by this is already infected. So even if you have recovered from the disease, in my model, you're considered to be infected, okay? So susceptible individual, infected individual, and each infected individual will be characterized by its age of infection. And the age of infection is just the time elapsed since the infection's onset. So if your age is 1, this means that you have been infected 1 day ago, okay? So now how do I describe the life cycle of the virus if I get infected? Well, I just assume that every individual is characterized by a certain stochastic process that I call the life cycle process or the life process, okay? And well, the time parameter is now the age of the infection, right? So X of A is just the class visited at age A by a certain individual. So for example, if you have a death trajectory, then after infection, you're exposed, then you're pre-symptomatic, then you develop, let's say, a serious condition. After a few days, you get hospitalized, and then you may die from the disease. And what we also, I mean, from the data we collected from the epidemics, and obviously people collected a lot of data, what we also noticed, by we, I mean like other people, is that typically like the time you stay in each of these compartments is not Markovian, right? So you don't want to assume that this life cycle process is Markovian. Typically, what people do when they do some inference is that they assume that you wait for a gamma distributed waiting time, okay? Okay, so far I just told you what happens once you get infected, but of course now I need to get to the description of how like the disease will spread in the population. So this is what's in this slide. So I will assume that I have a population of size n, okay? So you want to think of n as a large number. And each individual will be characterized, so each individual X will be characterized by 2 coordinates. So the second coordinate, like this X sub little x, is this life cycle process that I described before. So it could be like a non-Markovian stochastic process evolving with the age of the infection. And the first coordinate here is a point measure, it's a random point measure that I will call the infection process, right? So this point measure is basically telling you at which point in time you contact someone uniformly at random in your population. So let's say this random measure as an atom at 1, then here is what happens. So you basically send a propagule and you pick one guy uniformly at random in the population. So at time 1, at age 1, you contact someone chosen uniformly at random. And then 2 things can happen. If this guy is already infected, then nothing happens. You cannot have like double infection, okay? But if this guy is susceptible, then this guy gets infected, okay? And so on. So again, 2 coordinates, life cycle process, and a point measure, a random point measure, corresponding to the times of infection. And here, time corresponds to the age of infection again. So let me emphasize that this pair of random variables can be anything you like. I mean, there could be like some very high correlation between those 2 random variables. They have to be independent for every individual, but the infection measure and the life cycle process can be highly correlated. So for instance, I mean, of course, if you recovered from the disease or you die from the disease, then you're not infectious anymore. So actually, in most of the cases, you will have some very non-trivial correlation between the 2. So as I said before, this is a fairly general class of model. You can recover like all the classical model. So if you think a bit about it, it's quite easy to guess what should be P and X in order to get SIR, ECIR model. You can allow for different age classes. For instance, if you want to assume that children are less infectious than adults. And you can also assume that the model is non-Markovian, right? If you assume that here, this P and this P is not Poisson, and this X is not a Markov process. You wait for gamma waiting times in each of the compartments. And so again, it's not really a model, it's a class of model, and it's the most general like epidemiological model you can think of with, I mean, one serious restriction, which is that you have no spatial structure, right? So the main assumption here is that once you contact someone in the population, you have to choose this guy uniformly at random. I mean, this assumption can actually be a bit relaxed, but well, again, at least in the description I give here, you need to have, you need to remove space from the picture. Okay, so how does it relate to branching processes? Well, if you're familiar with Crampmatt-Jaeger's processes or generalized branching processes, then this can be reformulated as a generalized branching process. Okay, so P corresponds to the Beers measure, X corresponds, like in the terminology of Jaegers and Nerman, to a random characteristics attached to each individual of the population. And the complication here is that your branching rate somehow depends on the population size. You can have some saturation effect due to the fact that if you contact someone which has already been infected, then, well, this guy will not be infected twice. Okay? So, just some convergence results in a nutshell. So here, again, we have like a fairly general model. At the microscopic level, you could have like very complicated correlations between the life cycle process and the infection measure. But at the end of the day, as you will see in a second, what will really matter is actually the intensity measure of this infection measure, right? So TU/DU is the average number of individuals that you may contact between time U and U plus DU. So why is it an important quantity? Well, in particular, if you want to compute a very important epidemiological quantity, so this R0, which is the average number of individuals that you contact along the course of the infection, then you take this intensity measure and you integrate it from 0 to plus infinity, okay? And the main assumption, and this is actually the sole assumption here, is that this R0 has to be less than infinity. Okay, so on average, individuals will only contact a finite number of individuals. So now what we can prove is the following. So first of all, we can prove convergence of the age structure of the population. So what does it mean? Well, if I define NT of ADA as, well, the rescaled number of individuals with a certain age in a time window DA at time T, okay, so you just count the number of individuals of a certain age. So this is a random quantity. But when you go to the limits, and by the limits, I mean when n, the population size is going to plus infinity, then this quantity is converging to the solution of the Mackenrich-von Förster partial differential equation, which is written in red here. So if you're not familiar with this PDE, let me just give a brief description of what it says. So first of all, the differential equation itself doesn't give you too much information. I mean, if you look at this equation here, this is a transport equation. And if you think a bit about it, it's just telling you that the age of each individual is growing linearly with time. Okay, so it's not so interesting. Now you have to prescribe the boundary conditions. So first you have a temporal boundary condition. You just assume that you have a fraction x of infected individual at time 0, and that the age structure of the population asymptotically is given by a certain probability density that I call G. Okay? So now the interesting part is the spatial boundary condition. Okay, so this is this NT of 0. So NT of A is, roughly speaking, the number of individuals with age A. So NT of 0 is the number of individuals with age 0. So this is the newly infected individuals. Okay. So now how do I compute this quantity? Well, so first of all, I will compute the average number of propagules, of virus propagules, which are sent in the environment. So how do I do that? Well, first of all, I condition on the age, I count the number of individuals with age A. So the quantity of those individuals is NTA, DA. And then I multiply this by the average number of contacts for those individuals, which is exactly the intensity measure. And then I integrate over all the possible ages from 0 to plus infinity. Okay, so this is the number of propagules sent in the environment at time t, given a certain age structure at time t. So now, because of saturation, every time there is a contact, this contact becomes effective if the contacted individual is susceptible. So if I want to get the number of newly infected individuals, I need to multiply this BT by the number of susceptible, S of t, and S of t is just 1 minus the number of infected, which is given by this integral. Okay? Okay, so again, if you look at the age structure of your population at a given time, when n is going to plus infinity, you have convergence to the classical McHenry-Confessor PDE, the nonlinear one. Okay. And now if I want to get the number of compartments, so NT of J, which is the number of individuals in stage J, then what I do is that I just compute the probability to be in I in age A, and I average this over the age structure of the population. Okay? So moral of the story, even if at the microscopic level you start with something rather complicated, at the end of the day, if you look at the epidemics at the macroscopic level, only a few parameters will matter. So first of all, the age structure of the population will be completely determined by the intensity measure of your infection measure. And then you can recover the number of individuals in each class by averaging the age structure over the one-dimensional marginal of the life cycle process. Okay, so at the end, I mean, this is not so surprising, but all the correlation basically disappears. And what you need to figure out from an inference standpoint is this average infection rate and the one-dimensional marginal of the life cycle process. Okay. So this is like a more formal description of the theorem. So what we do is that we look at the empirical measure recording the age of the compartment for every individual. And what we prove is that at the limit, this empirical measure is converging to a product measure where this NT of A is the solution of the McHenry-Confessor PDE. And this is the one-dimensional marginal of the life cycle process. Okay. Maybe a few words about the connection with the literature. So what is fair to say probably is that, like more often than not, when people are dealing with many compartments, what they do usually is that they assume that you have some Markovianity and you can write like a master equation. So what you get is a system of nonlinear ordinary differential equation where the dimension is more or less like the number of compartments, probably the number of compartments minus one. And what we want to push in this approach is that there is probably like a better way of looking at things where like you first describe the age structure of your population in terms of the solution of a PDE, and then you decorate, okay, this partial differential equation with the one-dimensional marginal of your life cycle process. So what you see in this slide is that our approach is between quotes, and for a good reason. Well, what we realized quite quickly when we started working on this project is that actually this model was already studied before, but it was actually the first epidemiological model that has ever been studied. So if you look at the original article of Kermack and McKendrick in 1927, where they introduced the SIR model, they actually start with this macroscopic description of the epidemics using the age structure of the population decorated with the one-dimensional marginal of the life cycle process. And as a side note, they just argue that the SIR model is a particular example of this type of model. Again, so what's I think kind of interesting is that many works who followed this seminal work of Kermack and McKendrick mostly like focused on the Markovian cases, right? So convergence to the SIR model or to the SEIR model. And so what we think is that given the complexity of the current pandemics, there is probably like a good incentive to kind of go back to this first approach. Okay. So let me briefly talk about contact tracing. So the main motivation behind contact tracing is the estimation of this tower view, so the intensity measure of the epidemics that I was talking about a few slides ago. So typically what people want to characterize is this probability measure. So tau of u divided by R naught, the basic reproduction number, so that this is a probability distribution. And so the general idea is to try to infer this quantity by estimating to estimate this quantity from reported pairs of infection. So what you do is that if you have been infected at time t, you trace backward in time the chain of infection, right? So I was infected, so this is what's shown on this diagram here. So this arrow means that A has just been infected, okay, by this B individual. Then you go backward in time to the time of infection of this B individual, and so on and so forth until reaching a reference time 0 for the epidemics. Okay, and so what you hope for is that the successive time of infection along the contact tracing data will give you some robust estimates of this generation time distribution. Okay. So how do you write this down from a mathematical perspective? So what I would like to introduce here is the chronological chain associated to individual X. So this chronological chain is just a discrete time process. So time here is not really time, but it's just an index for the ancestors. So R of L is the time of infection for the else individual, for the else ancestor of individual X, ranked backward in time, right? So going back to my previous picture, so I take individual A, it was infected at time t, then my chronological chain at 1 will be at the time of infection of the infector of my infector, right? So this is this time here. And then I keep on doing this until reaching time t is equal to 0. Okay? So for every individual X, I just go backward in time and report the time of infection of my ancestors. Okay? So exactly as before, I would like to look an empirical measure associated to this, that I call the historical process, right? So I just define h of n as this sum, right? Where like I just report for every infected individual the chain of infection. Okay, so it turns out that there is kind of a nice description again of this quantity when n is going to plus infinity. And this quantity can be actually, again, be described in terms of the solution of the McKendrick-von Förster PD. So how does it work? So it will take me 1 or 2 slides. So first of all, what I will show you is that when you go to the limit, then the typical chronological chain of an individual chosen uniformly at random will almost look like a renewal process. Okay, but there will be a slight twist. So first, let me describe what is the renewal process, which was introduced in the CMJ literatures by Jägers and Nerman in '84. So first of all, you describe the Malthusian parameter, okay, of the epidemics as the following quantity. Okay, and I mean, this has an intuitive meaning. So if you look at the onset of the epidemics, when the number of susceptible is small, and if you assume that the R0 is strictly greater than 1, then this alpha is giving you the rate of the exponential growth at the onset of the epidemics. Okay, so alpha is the Malthusian parameter of the system. So this is quite a standard like quantity in the CMJ world. And then once you have this alpha, you define a renewal process starting from t at time 0. So t is your time of infection, and decreasing according to those increments which have density exponential minus alpha x tau of x. So you see that alpha was chosen in such a way such that this is now a probability distribution. Okay, so again, like your chronological paths will start from t, will make negative increments because you want to record the time of infection of your ancestors. And those increments will be distributed according to this density here. Okay. So now back to my historical process. So I want to assume that at time 0, there is a fraction x of the population which is infected, and that there is an initial exponential x structure. It doesn't have to be that way, but it makes the statement of the results a bit nicer. We can actually generalize this to more general initial h structure. And so if you want to get a typical historical process, you take this renewal process, but now you kill it. Okay, so you assume that if this historical process is at site x, okay, you just kill this process with probability 1 minus Cx S of x, where S is the number of susceptible in the McHenry-Van Perster PDE. Okay. And so what we can show is that there is convergence of this historical process to this quantity, where inside this integral, what you have here is the law of the kill process conditioned on survival. Okay, so roughly speaking, what this is telling you is that if you pick one guy uniformly at random in your population, which will be eventually infected, then the ancestral process can be described by a renewal process, a killed renewal process, but conditioned on survival. Okay, and you see that you kill with a probability 1 minus C, so sorry, there should not be a C here, 1 minus Sx, okay? So in particular, your renewal process, because of the conditioning, has a tendency to visit sites where the number of susceptible is high, okay? So this introduces a bias where infection tend to happen at times where the number of susceptible is quite high. Okay, so just to summarize what I just described, so we started from a general epidemiological model, so it's more like a framework with an arbitrary number of compartments. And so what we could prove is a law of large numbers. So we gave a macroscopic description of the general epidemiological model. So the H structure is just the solution of a McHenry-Van Perster PDE. And if you want to recover the compartments, you have a decoration of the PDE, so to speak. You can do some contact tracing as well, not only describing the number of individuals in each compartment, but also the genealogy of each individual. So the H structure is obtained by a certain conditioning of the renewal process. So here I started from an exponential distribution. If you start with a more general H distribution, this is an H transform, which is completely explicit. And something I didn't have time to talk about, if you want to describe not only the H structure along an ancestral path, but you would like also to describe the different compartments, then there is a way to do that exactly as what we did for the macroscopic description of the epidemiological model. Namely, we can decorate this conditioned renewal process using some PAN decoration. And with this, I think I'm done. So thank you.
Thanks very much, Emmanuel. So does anyone have any quick questions? Yes, Zhenyao is.
Okay, so sorry for the maybe naive question, and maybe I should know this from Felix's thesis actually, but so if you discrete this time and you think of the state of non-zero as its age plus its compartment, do you get some sort of infinite type, multi-type branching process? And in that case, could you see your convergence result to an age structure as some sort of this root Kreinmann, this kind of Perron-Frobenius kind of theory, so you have your Maltesian parameter, which is kind of which gives you the growth or decrease of population, and then you have this limit measure, which is like an eigenvector. Is this a way?
Yeah, I think there will be probably a way to do that, but and this is actually something that I mean, if you look at very carefully some of the papers of Jaegers, there is some. I mean. They do something quite similar to that, but I think it makes the formulation a bit messy, right? So, yeah, but there is a way actually to see that as a multi-type branching process, but this is probably not the most natural approach, so to speak, right? Like,
yeah, because
there is probably a way to do that.
Well, that's interesting, because I mean, maybe once you have this multi-region parameter, and once you know that then the convergence is almost automatic once you have a spectral gap, right?
Yeah.
Okay. Yeah, thanks.
And Pascal, you also have a question? Or is your hand just? You're muted.
I have many questions, but I will ask only one. So about how to recover the compartments from the H structure. So you use the fact that, well, you just look at conditional probabilities. What's the probability of being in a compartment given the age? But why is this invariant in time, this probability? I mean, this is only this would only be at some stationary state, right?
I think it's asymptotic, no?
You mean like the?
Yeah, I think you had it. Sorry.
Yeah, here, right? Here?
Yeah, yes, exactly, right. So this probability would, in general, also depend on t, right? And on the initial condition of the PD, etc.
Not really, right? Because you are talking only about a single individual. So you assume, I think, like the main assumption here, which could be discussed actually, is that the life cycle of each individual is completely independent, right? So once you're infected, the course of the infection is completely independent from the rest.
Yeah.
Right. So I think I mean, at least heuristically, it only follows from the independence of the different life cycles for the individuals composing your population, probably.
So this is assuming we start with just one.
No, okay. So that's
we start with no initial age profile, right?
Yeah. Well, so no, actually, that's a big question on its own. So here we assume that we start with a fraction of infected individual X, which is strictly positive. So we don't start with a single individual. And we assume that there is an asymptotic age structure from the population. So now an interesting question is what happens if you only start with a single individual and you let the population evolve until you reach like some sort of like between quotes stable age structure of the population. And so we could not do it for the moment, but in the PD literature actually there is a big chapter about this called the renewal solution of the McHenry-von Foster PD.
So there is, okay.
Yeah.
Okay. I will take other questions offline and follow up on this. Thanks.
Okay. So great. So let's. I think it's probably time for the coffee break, but let's thank Emmanuel again for his talk. And I don't think we gave a proper clap to Zhenyao before, so maybe we can give a clap to both of them if we unmute.
Thank you.